Okay, this talk is about malware analysis with radar, of course. But this is an introductory talk. We are not going to analyze a very complex malware sample here. This is more for those who want to start using radar and analyzing malware. And I prepare a demo, a custom malware that I have coded in order to analyze simple things. So first of all, who am I? My name is Pasamar. I'm DFIR consultant for 16 years, so that means I'm quite old. I founded a company in 2005, and I'm CEO, so I do a lot of things in my daily basis, and I speak to clients. And I'm not a reverse engineering professional, not an expert. I do not consider at all. But we have sometimes we analyze malware in our incidents, especially Windows malware. So it's part of my job, a partial part of it. Also lecture at the University of Catalonia, Polytechnical University, UPC, and I am professor there. Well, what is the objective of this talk? The main goal is to show you how to analyze Windows malware with radar, but also to show you the beauty of the reverse engineering process for those who want to start doing that. The outline is very basic. We are going to review the disassembly concept as some fundamentals, and also some tips about malware concepts. And then the second part is all the analysis of this binary. So in this demo, we are going to do it live, the analysis, some part of them, because it's impossible in a talk to analyze the full malware. But we will see I will give you some tips or some ways in order to start analyzing a malware in Windows with radar. Well, first of all, reverse engineering process is the process of deconstruct and extract knowledge of this object that is a man-made object. In this case, for example, a malware binary. And this assembly is a great tool to analyze compiled binaries, of course. So as a part of the malware analysis process, this assembly is a static advanced technique we can use to do it. During the demo, I will only do static analysis. We are not to debug anything. So debugging means executing malware. So it could be dangerous, even if you do it in a very controlled environment. This malware, if you are debugging, is executing. And sometimes you say, okay, it's a virtual machine and nothing happens, but maybe it can get the MAC address, your IP, your user, any important information and exfilter it and use it later. This information can be used, for example, to know if this malware is in a sandbox or in a analyst machine. So it's better at the beginning if you have not a very very good skills at the beginning to do only static analysis. With static analysis, there will be no problem. And it will help everybody to understand better what the malware is doing. I recommend everyone to start with disassembly before debugging. It's the best way to understand it. Well, before jumping to disassembly, let's review some fundamentals. For example, about the computer architecture, we have to review, or you have to review to start the architecture of the Intel in 32 and 64 bits, also registers, flags, and memory. especially what is stack, what is heap, what are local variables stored, etc. We are going to review this a little bit later. Important how memory map works, so how in a process the memory is stored and how it grows in one way or another. Okay, these fundamentals are important to be reviewed. For example, let's see this example to know if everybody knows where the data is stored in the different sections and memory. For example, fix only on the string side. This is, for example, a constant string. Does anybody knows where is it stored in memory? Well, it's stored in earth data. This other, for example, any help? Data, okay. This one? Is earth data. Why? Because the pointer is the variable that has the address, but you declare a string that is fixed in earth data, and we are going to see it now. And this one? Okay, stack. And of course, this is heap. Okay? It's important to understand this concept because otherwise it's difficult to follow this assembly and understanding where each variable and each string is located. Okay. So in this example, for example, we take a look now at earth data, and there we have our by r2con string, okay, and the pancake string too, okay. This is in earth data as we said before, and in data we have here this other string that was this ri, okay, and this is stored in data, okay. Well, it's important at the beginning to take a look at the sections and see where the variables are located. Also, these concepts is very basic, but and you need to have a broad understanding of this, of the compilation process and linking process. Okay. Well. It's not so important. Okay, P file. We are analyzing malware binaries, so it is a very specific binary type that is based in an old Unix format. Okay, and a P file has some peculiarities that it's important to know. Basically, has a lot of in common, for example, with the sections with an ELF binary or so, but there are some differences, especially in the header. Okay, it's very important to know that any binary start with this. Is there any water here? Sorry, okay. Water. Okay, now. The magic number, these M set letters, okay, this is a signature. This is because of the first developer, Mark Swinovsky, that develops this MS2 format. And there is an MS2 stub for compatibility that says the typical, this program cannot run in DOS mode. Okay. You have to learn a little bit about PE format to fully understand or to do malware analysis. Okay, I go a little bit fast because we have a lot of things to do. Sections, very important. Text section, executable code, initialize data in data, earth data, read-only initialized data, and the resource directory. Okay. Where you can find images, icons, and maybe another executable embedded or something like that. Okay, important to take into account, we can check sections in Radar. Thank you. And very important to see that there is permissions, okay, of each section. It's important to check these permissions in order to see if there is something strange. The typical text section where code is located should be only read and executable, or should have only these permissions, but sometimes it has written permissions, or if it has a W there, means that maybe it's going to modify itself, and it could be a typical malware behavior, for example. Well, why this permission? Also, the alignment is important to understand this. In the image in disk, the binary has 200 alignment sections, but in memory it's mapped to memory pages, so it's aligned to this size, and you have an alignment to 2000 bytes in memory. It's different. So when you dump a binary, you have to take this into account, because it is not the same in memory as in disk. Okay. Well, and now the most important part is recognizing C code constructs in assembly. When I teach this in the university, I see that many people has forgot completely C code, but it is important because malware is usually written in C. So it's very, very, very important to recognize this. Okay. Oh, sorry. Well, the best way, with no doubt, is do or code your own small programs, tiny programs with an if, a while, a case, switch, etc., and then disassemble it, so you can understand each part and recognize these constructs, and then will be much easier for you to do this, to do malware analysis with real samples. Okay, I do it generally. I work with OS X, so I use cross-compiling, and I compile it for the Intel architecture and in Windows, and doing from my OS X machine. So no problem. You can sometimes execute it if you are completely sure that this is not malware. So let's go on. Okay, this is another Harpoon Pointers. This is the same example as before, and we have here this string in air data. So this string, because it has this null character at the end, this is a char pointer. That means that P points to the first char of the string, not to the string itself. It points to a char. And P is basically a special variable that stores an address. Okay, let's see here where it is. It's here, okay, and pointing to this address. Okay, basically that's it. You can have later. You can take a review of everything, so you can see how it works. But it's important to have these concepts. So global variables, for example, this int, okay, we modify this int in the code. If we take a look at the data section, we have here this 7 we have initialized before, and in main function we can see here this modification, and look at how it is addressing this this memory address. Okay, so it's moving 8 to this address that is in data. Okay, and so on. So we can continue. Let's go to a little bit faster because I have a lot of things to explain. But it is important to follow all this process and understanding how it works, how all the arguments are used. And we will review also the stack frame now. An if statement, for example, it's a very simple example. It's comparing two integers and returning one or the other. And it's important to check how it does this comparison, this check in the code, where it jumps, okay, and how every construct works. Okay, I will go a little bit faster because it's theory. In visual modes is a very good tool in order to see how the code blocks are organized, and you can see the flow much better. Okay, it's very interesting when you have these cases to full understanding what is happening in each part of the code. Okay, well, this is a for. Okay, here we have this this jump here. Okay, the first time, and we have here this comparison is comparing EAX with this variable, and basically is comparing if E is less than 8, and then jumps there. Much more easy to see it here, but it's very interesting to see or to recognize this kind of loops, okay, typical from the for, while, and do statements. Okay, the same with while, etc. Better in we will see it better in here in the visual mode. First I jump. Okay, this code is not before this other code here, but in visual mode is organized much better, and you can see where the jumps for the first time goes, and it returns back to this address. Okay, okay, and so on. Many examples. You will have the slide, so you can work it at home. Okay. Important to understand calling conventions, caller and callee, and okay, we will see just an example. Sorry. Okay. Well, there are different calling conventions because I'm using here MinGB is using CD ECL, so we are going to review it. Okay. This is the C declaration. Well, these are basically arguments are passed on the stack in 32 bits, and the return value of each function is in EAX register. This is important to follow after the demo. Arguments are from right to left. And in the new versions of GCC, there is an alignment in the ESP register, so to 16 bytes. So the first byte is an AND with 0. So each direction of ESP is aligned with this boundary. Okay. Okay. And color clean. Okay. Sorry, this is important. Well, this is the example. It's a very simple example to understand the stack frame and the calling convention. Well, this is the prologue of the function, the preamble or prologue, and these instructions are put there by the compiler. Okay, this is mean. Okay, this is the alignment we have talking about. And how it works. Well, we are calling sum with two parameters, 1 and 2. So they are is moving into the stack. How radar explains this or represents this? In the disassembly, we see the ESP. ESP is the top of the stack, and for H is ESP plus 4, so this is the second parameter. That is more or less the graphic to understand it. Okay, and finally this is the call. Okay, and when we go to the function, when we enter this sum function that is adding these two values, we have this situation. Okay, ESP, the return address that is there pushed into the stack, and the parameters are there. And this prologue here of the function, okay, means that we have to save the state of EBP. EBP is there, and we have to save it in order to save the stack of the previous function. So this old EBP is pushed there, and ESP now is there. We move EBP to ESP, so the new EBP will be on the top of the stack now. And because there is no local variables, there is no movement of ESP. There is not any memory reserved in stack. Okay, in this case. Well, basically you have all these pictures to follow the whole process later. So, well, if more or less you understand it, we go on because we will see this in the code. Okay, and the leave instruction is important because, as we say, in this calling convection, the main function, the caller, has to clean the stack. So it is the same as these two instructions. Okay, it's moving ESP back and popping the old EBP, and then restoring the old stack frame. Okay. Well. Last slides. Oh, sorry. We need to pay attention to different behaviors of malware in order to understand which sample we are analyzing. For example, if there is a internet connection or not, is downloading something or is dropping a binary and so on. Okay. So. Malware can be a downloader, a launcher, a backdoor, stealers, keyloggers, and we will see these differences when we analyze the code. Okay. Also the persistent mechanism. Okay, if there is some Windows registry keys or something like that, or it is trojanizing binaries in order to start with those system binaries, or the DLL hijacking or something like that. Okay. Important to know the APIs, the Windows typical APIs that can be present in malware. Okay, and at least this important part, that is data encoding. Okay, data encoding could be common cryptographic algorithms or custom ones, or the typical Caesar or Shor or ROT or something like that is commonly used, and also other encoders like B64 or a custom one. Okay, we have to recognize this in the code. Okay, so let's start with the demo. Sorry, it was. Where's my mouse? Okay, so first of all, we have our malware sample, and we are going to load it with radar. This is AX. Okay. Well, a first step, for example, could be if the malware is encrypted or not. It is packed. Is there any packer here? For example, we can check the entropy. I will load it without analyzing it. So this is not the PE. This is the zero offset of the binary, and so I can check the file entropy, for example. This is 5.57. This is quite standard entropy. to know which values are typical or not, it depends. Over 7, there is probably some kind of compress or encryption. 5.6 is okay. It's a mix of strings, zeros, and code. So it's quite normal. So maybe here we don't have any packer here, but we don't know for sure. Other way to know that is to do so without entering radar with this. With this command in a one-liner and doing the same. Okay, it does not work. Oh, sorry, I forgot to go. Okay. Sorry. NC pH entropy. Okay. Good. Missing file, yeah, of course. Okay, it's the same value. Okay. If we load it into radar, we can check also entropy here, but it will be better, for example, to check sections entropy now. Okay, we have the sections with ES, and we can check the entropy of the sections in order to know if there is any section with a high entropy and maybe some data encrypted there. Doesn't look, are not very high values, so I guess there is no, for the moment, there is no packer used or any lot of encryption here in this file. Okay, so let's check the header. For example, we can do so and check the header or so, or just E and check the most important values. So, for example, here the architecture x86 and 32 bits, okay, compilation time and so on, okay. This is good in order to have a fast understanding of the binary. Now we take a look at the sections again, and maybe we can review the entropy. As I said, we can check it this way. I forgot to tell you. For example, here we can check the section text, for example, it's the higher entropy, and we can have these bars, graphs, and so on, in order to check how. If you see a very high and constant entropy, then means it could be encrypted. Okay, so let's take a look at the imports in order to see which external functions from the Windows API the malware is using. So we can check it with II, sorry. And well, we see here some peculiar functions, APIs that is using. This malware wants to do something with registry keys. So it will check and create keys, apparently. And this is a first warning. Okay, maybe this will be, this is done for persistence, for future persistence in the system. Okay. We can see here interesting things like, for example, here we have sockets at the end, you see? Socket, send. These are typical APIs to have a socket communication, or maybe to read the IP address of the system or something like that, okay? Also, get name and get host by name is the same. Connect, okay. Typical from this API to start this interface in Windows. Okay. We have also string copy and string len and string comparisons. Okay. But it's interesting. We have here some message box. Well, malware should not use this very much, except in some ransom cases, okay? But malware used to be very silent and hidden, but here is some message box. We don't know exactly why, but could be a good idea to check why the malware is using this function in order to communicate something to the user. It's interesting. Okay. What else? Standard C functions. Okay. For now, it's okay. We have. Okay. This is interesting too. These APIs are typical to know the processes that are running in a system, and is checking and iterating this list of processes in order to check something, and we will see if we can explain what this is, what is it, or a sleep here. Okay, we have with this information we have an understanding of what the malware can do, but we are not completely sure. Okay, this is very basic analysis. Okay, so strings. Strings are commonly used by malware to use these strings in order to check something or to communicate with a host or something like that. So we are going to check it with EZ. We check the strings here, and we have interesting strings. The first one is very, very interesting. Well, this get host name is because the first string is not a string; it's a table, so has not a null character at the end, and is mixing the two strings. But the string or the table is from ABC to this slash. Okay, what is this? This is typical from B64. Okay, a B64 function that is here in this malware, because we have not seen any API using B64, but this string is telling me that maybe the malware has a function in his code that use B64. Okay, the other strings here, for example, is interesting because process found. Okay. Process found, what does it mean? We have seen that it's using some APIs to check the processes, but it's not very typical to write something in the terminal or in a message box saying process found, because it's malware. Okay, let's see in a further analysis later. Okay, here is some kind of process. Maybe it is related because it's very near to this string also. Okay. And what is this? These are a lot of strings that are using B64, so could be related with that. And we will check if we can see what are these strings hiding. Okay. Okay. All these strings are from the compiler, so no problem with this. Okay. Basically, the main information is this one. Okay. It's a very simple malware sample, so it's not very, very complicated. It's better for this kind of purpose. Okay. So let's see if we can decode, for example, one of these B64 strings. We have the address here. Wait a minute, my mouse. It's crazy again. Oh, here. Sorry, with the lights, it's very difficult to see. Okay. Well, I have selected this. Okay. This is in 405087 virtual address. So let me 405087. 405087. And maybe we can tell radar to print it. Okay, if very easy way, for example, we can do so with whole line and see what's there. Oh, sorry. Okay, this is the string, okay? If we go there, we seek that address. Sorry for that, but it's complicated. Yeah, here. Maybe we can do this, P6D, and this will decode the string at this address. But unfortunately, there is no text there. There is no string. So at this moment, we know that probably is using some kind of encryption, the malware, before encoding it with B64. So we will follow some steps. So, okay. Well, if we take a look at the sections, for example, this way, and this one, we have here all these strings, and we can check the addresses. And for example, we can look at this data section, and it's very interesting because we are seeing a lot of @ symbols, very aligned. Okay, a lot of them. This could be the pointers to the string, or maybe a struct that the malware is using in order to handle all these encrypted strings. Okay. Well, it could be a struct. Okay. Well, what else? Other hints or other things we could check in order to analyze this. Well, we can maybe starting having a global overview of the functions of the. We have checked sections. We have checked for now the import APIs and so on. Let's go to see the functions. Okay. Well, if we go here, we seek to main. Of course, we can PD print disassembly some instructions, or PDF. If Radare recognize the function, we will have this. So let's start the hard part of the disassembly now, and we will try to understand what this main function is doing, and I will analyze 2 or 3 functions because it's impossible to do with all the functions of the malware in order to have a better understanding. Okay. What is very important is to understand how the parameters are pushed into the stack and passed to each call, to each function. Okay. So let's see. Let's start with the main function. Okay. Here we can use the visual mode, and it is a good idea to use this view to recognize loops and the whiles and for statement we have been talking about. So we can see if there is any loop here. Of course, you can see one, okay, a loop here, and we see here a movement of this 0 to this variable. Okay, only a byte. When you see a byte here at the beginning and is testing this byte after the 0, you can take a look at the end and see how at the end of this loop sets a 0 to this variable. Okay, so it's set to 1. It's compared with I confused the variable. No, this is set to 1. Then is compared here to 0 with 0. Sorry, and at the end, because this is not 0, it jumps here, and at the end is set to 0 at the end of this loop. But before this second loop is in this first loop here. Okay, so this is some kind of Boolean variable, true false, that is using, but the type here that radar is indicating in this disassembly analysis it's an integer, of course, it's also right, but we can set this this type to a Boolean and rename the variable, for example. So there is a loop, and the loop starts with 1, is true, and at the end of the second loop is 0. So we can call this variable stay, for example. We can rename the variables here. So here, AFBN is used to rename the variables of this function. Okay, I will increase. Yep. In this case, we want to say, for example, we will call this stay. This is the new name, and var98 is the old name. And if we want to change or to tell rather that this is to the disassembly that this is a Boolean variable, we have to use AFBT. Okay, and we say stay is the name of the variable now is a Boolean. Okay, now we can check if it works properly. Okay, so we have now this Boolean variable here. Okay, and if we go back to our analysis, we have now this comparison is better or much easier to understand. Move 1 to this Boolean variable and is comparing it here with 0. Okay, if not equal to 0 because it's 1 the first time, this is true, so we'll enter this loop. Okay. Yep. Well, go on. This, for example, is another kind of variable that is stored or is set to 0 at the beginning, and here, bar 10 here is adding 1 in this loop. Is adding 1 to this variable inside the loop, and is comparing always this variable with 539. 539 only some of you have very fast check. Oh, this number, I know it, because what is this number, 539? We can use, for example, from radar racks in order to know what means 539, okay? And this is lit. So it's playing with us, this malware developer, and is comparing something with lit. And, oh, sorry, this is not this main. Here. So this is like a counter compared here with 539, and if it is not 539, it is incremented in each loop. Okay, when this so this loop ends when it is equal to 539 and then enters this other loop. Okay, so but what is doing here when it's in this loop? There is a call to some function here. Okay, nothing else. So after this call is setting is pushing this value 3E8 that radar is indicating us that is 1000, and sleeping. This is sleeping 1 second lead times. Okay, so lead times are 20 minutes or something like that. That means that the malware is doing something during a lot of time, and when this time ends, is entering this other function. Okay, so what does this this function over here, this previous function in this first loop? Okay, if we go there to this function, we seek there PDF. Okay, there is another call here. We will follow it. And then here is a bigger function. Okay. At this function, we have interesting strings we have seen before. This process found, this process name, okay? And we can see that this create tool health32 is taking the snapshot and processing all the processes in order to know if one of them has this name. Okay? Well, what happens if found this exactly process that if it happened, the malware is printing, let me follow, here. Basically is printing this message, but this does not look a malware behavior. Why? It's a very simple case, it's a very simple example, of course, only for this demonstration purposes, but the idea is a general idea that it doesn't matter if the malware starts doing the bad things 3 seconds after execution or 20 minutes later. The malware is in a loop trying to do good things, good stuff, like goodware, not malware. So this is a goodware function, okay? We can say this is goodware function, and after the lead seconds, it will enter in other functions, so maybe there is the badware, okay? Let's get back to main, okay? Oh, I didn't tell you, I forgot something. To have an overview at the beginning of the malware, you can, for example, when you are in main here, you can use AGC, and you will have this call graph. Okay, of course, in the screen, it's a little bit complicated sometimes this because if you use the capital C, you will have the global call graph. It's warning us that it will be a little bit complicated. Pancake loves this this kind of graphs. Okay, but it's not so bad. You don't need to open Cutter now. There's a fast solution that is generating this, and in a very simple way, you have a call graph here at hand. Oops, sorry. The corners, okay? And you can handle it, and you can check. Well, not so easy. Need a bigger screen. So, well, we can look for main now. Here, no, sorry, this is entry 0. Main should be here. Okay. This is main, and we can check what main is calling, and main is exactly calling the previous call graph, but now we have the whole binary calls. But it could be very interesting at the beginning to have this graph in another monitor or print it and right hand or use your iPad to take some notes of the function. It's very interesting at the beginning to know where everything is, and it's quite useful. I use it. Okay. Now we go to the visual mode again in order to follow the second loop. Okay. The first one, remember, is sleeping, calling this goodware, and after this time is entering the next function. So the next loop. Sorry. At this loop, okay, we have different stuff here. Okay. Well, there is a string length, there is some malloc here. When you don't know exactly, or at the beginning you have some problems to recognize code, so take a look at the calls, if there are calls there, and the strings, and will help you understanding what the malware is trying to do. It's not so important to fully understand each instruction. we will have, so okay, the addresses, I need it, sleep. Oh, so, okay. Well, what is important here? That after some string length, some malloc here, is allocating memory in heap, and moving some section or some content of some address here. So we have some string. Is pushing the parameters here. Okay. So very important. Here is a call to a function that we don't know what this is. Oh, I forget to say that this is a stripped binary. So in a non-stripped one, when you do it yourself, you will compile it. If you don't strip it, you will have some debugging information. So you will see the name of this function. In this case, because it's stripped, you don't have it. But you can see here a call to a function. And before this, it's very important to practice what are these parameters that are being pushed into the stack. Okay? So, very fast. Okay. Okay. So we have some parameters here. The first one is always ESP because are pushed from right to left. So the first parameter in the function prototype is this last one, okay? This is the first one and is EAX. What is this? This is the content of this char pointer here. And what is this? It contains this, and this is EAX after a malloc call. So it has an address of some memory allocated in the heap. And how much memory? Okay, there is a string length before, and this string length is a string length with just one parameter. This is the string in this case, and this string is this here, okay? So what is there? 40, 55. 50, 45? I think so. No. I always forget that. 45. No, I did not properly. I have it here. So it's the QBT string, okay? This QBT string, let's take a look at this here. QBT. I saw it just a second before. It was here, yeah. So we have here, this is okay, was 40, 54. Okay, sorry. So it's allocating memory for this size, and there is increasing by 1, okay? And this malloc size is here at this pointer here, and then is passed to the stack here as the main or the first argument. At the beginning, it is a little bit complicated to follow, but please do this effort because it's very important to understand this. What resource you can use in Radar to do that? You can rename, for example, the arguments. How? As we said before, we can do this, for example, and we can say, okay, this is a malloc 5 bytes pointer, so this is arc8h, for example. Oh, arc. Oh no, I'm in another function, sorry. It was, sorry, PDF. this is the ESPX. Well, you can, for example, in this case, because it's that way, we can add a comment, for example, here, and say malloc 5. Okay? At what address? At this address. Sorry, I constantly lose my here. Okay? So we do so, and we will have a comment here. Does it work? No. What did I wrong? Oh, sorry. Typical mistake. Okay, here we have a comment indicating this is the malloc file pointer, okay, for example. And the other ones are the qbtt string itself, the pointer to this string. This is, for example, we can say cc string qbtt at 00040. How much sign do I have? 10? Would be 15? Okay. Well, that's the idea. 40, sorry, here, 25, and 23, for example. Okay, so we can set some comments and rename these variables in order to better understanding. And now what we have to do is follow this this call, sorry, to this function. Okay, in order to know what is happening here. Our arguments are this allocated memory and this string, and then a pointer to the old stack of strings that we have seen. But let's concentrate in these two first parameters, okay? Okay, now we have this. So we enter this function that use these arguments to call several functions. So here we have a lot of calls and parameters set to push to the stack. So you have to do the same with all these functions in order to understand what they are doing. Now we are going to accelerate it a little bit because we only have 10 minutes. So I have prepared a command list to execute in Radar. You can use projects, for example, to save all your state, or copy and paste all your commands into a file and use it, for example, at the beginning with this minus with -i parameter, and I have this command txt. So it executes a lot of instructions. Oh, something happened here. Oh, analysis. It needs more information. Okay. Well, now what happened? If we go to main now, there are all these comments set there. Okay, if we follow the function before, I have called it bad things. Okay. If we go there, there are new names for these functions in this case and some comments. Okay, this is a decode pass function, okay, because it's giving this pointer to this malloc allocated string and this string, okay. If we go there to this decode pass, sorry. Well, now what we have here, we have this this function, and we have a string copy. This string copy is copying to the destination, that is this malloc file, this string, okay? So now this pointer is pointing or contains the previous string. Okay, it's copying it to this string, and after that, as a single parameter, is pushing here into the stack and call this final function. Okay. Oh, sorry. And what does it? Okay, I have some comments here, but if it's the first time here in visual mode, I can see this. Okay, it is using this pointer in order to modify the content of each byte. Okay, but if you don't fully understand what it is doing, we can. This is the typical function we can emulate. Okay, so let's see here, much better here, these instructions. Okay, we have this prologue here. Then this is 0 set to this variable. Then is moving to EAX this parameter, so this is the string to modify, okay? Is moving the content pointed of the first char to EAX and is subtracting 1. So it's modifying each character, each byte, subtracting 1, okay? Because it's an ASCII value, it was the letter Q, then it will be the P, okay? It's modifying this string, and maybe it would be a password that will be used in the next functions, okay? But let's emulate it with a seal, okay? Okay, so we're here, and with a seal, we have to initialize it. Okay, we initialize memory. And then we can take a look at the registers. Okay, ESP, SVP are initialized because maybe we are going to use or we have to write something. We have to set EO cache to 1, true. Okay, so this will be only modified in memory, not in. We are not opening it in write mode. We are only enabling cache in order to modify in memory. Okay, let's go on. Okay, the only parameter we have here is, or the only parameter that is being used is this arc8, and this is a pointer to that string that is qbtt. Okay, so because we are only emulating this snippet, this piece of code, we have to set it somewhere. What can we do? We can use the stack, or we can use any memory that we want in order to write this string and set a pointer to this string. That is what we are going to do first. Okay. Okay. So if you remember, at 404000 we have the data section, and if we take a look, 4000. Oh no, sorry, no. 404000. Okay, we have this data section, and we have some space here for us. Okay, let's write there the script that the string that is going to be used. Okay, let's write it directly in memory. For example, qbtt, and we IT. Okay, let's check if it works. Oh shit. Well, I think in this case, for this snippet, this is not going to be used. Type something wrong. Let's try. What else? Well, okay. Well, yes, back to the function, sorry. And as you can see, arg8 is a pointer to that string. So we have to write this pointer anywhere because it's an argument. We can set it directly here using the AE commands from SEL, and we will set this address we have used to set the pointer, the string, sorry, and we set it here, where to EBP plus 8. And then do it this way. No. What did I wrong? Sorry. That's it. Yeah. Okay. Okay. And now I will check if this was okay. I will write this for ABP plus 8 parameter. Okay. It's a pointer to our string. Okay. Now everything is set up. So we can now emulate the whole function till this knob instruction, for example. So AP, because we initialize memory, is here at the beginning of the function, and we have set this argument that is the one that is going to be used. And oh, sorry, this I forget to. Okay. Yep. Well, we can step until the end of this code, okay, and it does not work because I crash the memory somewhere. Let me do something. Once again. Okay. There was a typo in the address, sorry. Okay, once again. S the function 0.0.0.40.1f 7 PDF. Well, we are back again. Sorry. Hash. Okay. Good. Now seek here and initialize again. Well, okay, fine. Now I want to write the string again. Sorry for that, but in the correct address. Sorry, I have to check it. Section where we have space here. 4040 B0 is a good location. Right. Q B T T at 4040 B0. What was that? 4040 B0. What did I wrong? Oh, there is it. Okay. Now 4040 B0. I will copy it. Okay. Now back to SEL, back to the code, and now we have to set the argument again. E. Okay, ABP 8. Oh. A00 40 B0, sorry. B0 ABP 8 plus It's no. Here, okay. px4 at EBP plus 8. We have it. Okay, and then we can do it again or try again. Now AESU till this address here. What is happening? There's a bug in SEO. Okay, now it's not working, but it's very easy. It worked many times. Well, because I want to follow a little bit, if you set properly the addresses, you will see here this loop will modify this memory, and you will see the pass string here. So pass is the password for something that comes later, and this is the encryption functions. Okay, these encryption functions are calling or are passing the strings of the struct, all these base64 that previously is encrypted with another function. Which function? If we go directly to check which encryption it is using, if we go to this address, 4016BB, yep. Okay, I have renamed it already, but you can see that all these two functions are part of RC4 algorithm, encryption algorithm. So if we take a look, for example, at this one, how can we know? Sorry. How can we know this is this algorithm? Well, maybe here is better. You can find here this, for example, this first loop that is generating the tables till 256. So it's generating the tables here with a little bit of experience, or if you are a squatter, you can do it dreaming. The recognition of this very fast, but if you take a look at the function, you know that it could be an encryption algorithm, and it looks like a KSA algorithm. That is the first part of the RC4 encryption function. So what next? Because we have not many time, I will show you two ways to decrypt these strings, and it's more or less the end of the demo. One is with this iteration, the struct that we have seen. Oh, sorry. The corners. The struct. Sorry. If we print here 64 at this address, we have all these strings here. Okay. So. No. Sorry. Once again. Okay. We have all these pointers to this struct, so we can print using this other option, print a word. So we can do it so, and iterating. This is radar scripting. Sorry, first I have to move there to seek the px. It will be easier. Seek, okay, and now pxw. What I want to have is all the addresses and all the strings we will need to decrypt it, and we are doing it so. Using, for example, this, I want to test if it works. 40, 40, 20. 40, 40. No. Yes, 40, 40, 20. Okay. Yep. Nice. Better so. Yep, that's it. Sorry. Well, if we do so and so and so, we can get all the structure. We can iterate very fast and have all the strings and the addresses, okay? And this is the base64 strings that is previously encrypted with RC4. And I go out and use a Python script. I have code for this, okay? I have a file with all the addresses and strings, and I want to iterate it and decrypt it here in this RC4 function here and print it. So the first way is, is a way to, where am I? Yeah. The first is a way to print it using radar scripting all these offsets, and then I have prepared this script to decode it and decrypt it, okay? This offsets, struct offsets. Okay, and then the magic is that we can see here the string that the malware is using, and well, the name that probably will use the malware, and it's a very common one, is svc host, and svchost.x is the name probably of the image in disk where it will be stored. This will be probably the registry key that we'll use, and after that there are some let's say Windows variables here, and process identifier and a domain. Okay, so maybe it is getting some system information and exfiltering it and sending. Where does it send? Pues, probably here. And at the end of the struct, there was an int, and this int is port 80. It's very easy to see that. And we can now check if it works. I will execute it in order to get the final string and see if it works properly. So let me... set up this, and I will execute with this malware. So it will not finish because we have to wait 20 minutes here. We have two options. We can patch the binary, or because I have the source code, we can compile it, modifying it. I will use this one at this moment. So here, as you can see, here, this is the lead iterations. I will set 2 for 2 seconds sleep, okay? And compile it again. So I have a quick sample, okay? Okay, it's done. Now, if we do this, we go here, we receive this string that is sent with the exfiltered information, and we can use, I have another utility that does exactly the same as the script, but in a different, that's not parse the file. So if we do so, okay, oh sorry, one. Okay, so we get here all these strings. It's using the same encryption and encoding in order to protect the strings that the malware is using, and the same encoding to exfilter this information using a simple socket to port 80, okay, with no protocol here. Well, I have a lot more things, but I think it's enough for a live demo. So thank you very much. That was all. And if you have any question, please don't hesitate to ask.
Any question? Okay, thank you.
Okay.